In this lesson, I'm going to cover sections 15.4 and 15.5 in your text. And basically what we're going to do is relate the acid-base reactions that I talked about in the last lesson to equilibria, which we just covered in the last unit. All right, so first just some definitions, and some of these are going to be review of things that you've covered before. But a strong acid is an acid that completely ionizes in solution, meaning there's none of the original acid left in solution. It's all broken apart into, for example, for HCl, it would be all broken up into H plus and Cl minus. You're not going to find any intact HCl in the solution. A weak acid only partially ionizes, so there'll be some of the original acid left and also some of the ions where it's broken apart. A monoprotic acid is one that only has one ionizable proton, meaning that there's only one H plus for it to lose. So then, following from that, a diprotic acid would be one that has two ionizable protons, or two H pluses that it can donate. And then a conjugate base, which again we've covered in honors, is what's left after the proton is donated. So in the case of HCl, the conjugate base would be Cl minus that you get when you're done. So because of our knowledge of equilibria, you should know that as acid strength decreases, which means that as less of the acid breaks apart, the stronger the conjugate base is going to be, because the more it will go in the reverse direction and want to pick up a proton. So let's write out an equation for this just as an example. So we have HF for an example. So HF is a weak acid, and as it reacts with water, you're going to get H3O plus F minus. So in this case, F minus would be our conjugate base because it's able to accept a proton. Okay, so the weaker HF is, meaning the less likely it is to separate out into its ions, the more F minus is going to be able to pick up a proton. So these two things are related to each other because of the equilibria. So as acid strength decreases, conjugate base strength increases. Now let's do a couple of examples of how we would write these chemical reactions and be able to identify the conjugate base. So HI is an acid, so HI plus H2O is going to react to make H3O plus I minus. All right, and in this case, our conjugate base is going to be I minus because it has the ability to accept a proton and go in the reverse direction. All right, HCN plus H2O is going to give us H3O plus CN minus, and in this case, CN minus is going to be our conjugate base because it has the ability to accept a proton and become HCN again. Okay, CH3COOH. So this is called an organic acid, and you will see these occasionally. And when you see the COOH group, that is the carboxylic acid group. That can donate a proton. So this is the H that's going to be lost. All right, so if we write the equation for this, it'll be CH3COOH plus H2O goes to CH3COO minus plus H3O plus. Okay, and in this case, this piece here where we lost the proton for, that's going to be our conjugate base because it's going to have the ability to accept a proton. So this is just one of those groups you're going to have to learn is able to act as an acid because it looks a little different than most of our other acids. The inorganic acids, for the most part, have the H written out front, but the organic acids, it's usually written at the end of the COOH because that's the carboxylic acid group. All right, so now that we have all of these equilibrium reactions, we would want to be able to express the equilibrium constant. So for acids, instead of Kc or Kp or Keq that we've been using in the last chapter, we use Ka, A just meaning acid. So this is the acid ionization constant, and it just tells you how much of the acid ionizes when it reacts with water. So Ka is going to be equal to the concentration of H3O plus times the concentration of A minus, where A minus is our conjugate base, over the concentration of HA, where HA is just some generic acid that we would be interested in looking at. Okay, and you can also write this as the concentration of H plus times the concentration of A minus over HA. So sometimes we write it as H3O plus, sometimes it's just H plus. Either is perfectly acceptable. All right, now let's talk about water. So you've probably already gotten the impression that water is a little bit different than other acids and bases. For one, it's amphoteric, so it can act as either an acid or as a base. And you learned or we went over again in the POGL that you did earlier this week, that it can react with itself and just make H3O plus and OH minus, or H plus and OH minus. So let's do an example of what the autoionization of water is going to look like. So here, water acts as both the acid and as the base, and there's nothing else present. So we have H2O, which is a liquid, plus H2O, which is a liquid, and that goes to H3O plus OH minus. So the first one here is acting as an acid, the second one is acting as a base, and a proton is getting transferred from one water molecule to the other water molecule. All right, so since we have this reaction, we can write an equilibrium constant for this reaction, and we call it Kw because it's the autoionization of water. Remember that we don't include liquids in our equilibrium constant, so Kw is going to just equal the concentration of H3O plus times the concentration of OH minus, or the concentration of H plus times the concentration of OH minus. Okay, so a solution that is neutral is one where we have equal amounts of H3O plus and OH minus, and you went over this a little bit in that POGL as well. Okay, an acidic solution is going to be one where the concentration of H3O plus or the concentration of H plus is larger than the concentration of OH minus. And a basic solution is going to be the opposite. So in a basic solution, the OH minus concentration is larger than the H3O plus or the H plus, however you want to say it. All right, that was a qualitative expression of acid or basicity of a solution, but we have a quantitative way to measure that as well, and we call that pH. So pH is equal to the negative log of the concentration of H3O plus. Okay, this is a pretty simple calculation. I know not all of you have done logs before. This is different than the natural log, which we did in the previous chapters. This is just log. And all you really need to know is that you do this just by using the button on your calculator. We're not going to have really complicated calculations with this particular quantity. Okay, one thing to note is that significant figures for pH are slightly different because the log represents an exponent. The numbers after the decimal are the ones that are significant. So, for example, if we have a pH of 3.00, that only has two significant figures because the 3 is just the exponent itself, and we have to have that placeholder, so it's only the numbers after the decimal that are considered significant. So a pH measurement of 7.32 has only two significant figures, so we only count the ones after the decimal place. Okay, the pOH is a similar quantity, but it's just the negative log of the OH minus concentration. Okay, and then the pKa is a useful quantity that we're going to use a lot when we get to buffers and titrations and things like that. And the pKa, as you maybe have noticed a trend here, the P just means take the negative log of the thing. So the pKa is just going to equal the negative log of the Ka, which is the equilibrium constant for the dissociation of the acid that we talked about on the previous page. All right, so this may seem like a lot. I promise we're going to do some examples and start doing some calculations, and hopefully things will all make sense.